So I'm going to be presenting our investigation into whether notch filters can enhance anomalous colour vision. So we've been focused on the Enchroma company, which produces sunglasses built with notch filters designed specifically to enhance anomalous colour vision. Existing research to date hasn't supported their claims, but still they have very emphatic customer testimonials, which I'm going to show you some of the most entertaining ones.
Okay, whoa. Whoa.
Is it red?
Yeah. Mm-hmm.
This is really red?
Yeah. Mm-hmm. Is that flesh color? That's human color?
So because there are clearly some exciting percepts going on, we thought this was worth giving a more rigorous testing to. So here you can see the cone sensitivities, the sensitivity curves of the cones found in normal colour vision and deuteranomalous colour vision. So colour vision is based on the difference between the responsiveness of the cones. So when you have, as we do in deuteranomaly, the sensitivities of two of the cones are overlapping too much, making their responsiveness more similar and therefore reducing the signal that's available. So you can represent colour vision in the McLeod-Boynton space, which is a physiological colour space constructed by comparing the responses from the cone classes in the same way that the visual system does with cone opponency. So in this space, you have the L and M responsiveness compared along the x-axis and the contribution of the S cone along the y-axis. It's possible to adapt this colour space for any observer. So here we have the deuteranomalous McLeod-Boynton space, comparing the L and L prime signal at the bottom and the S cone responsiveness at the y-axis. And this is an isoluminant colour space. Oh no, sorry, wrong thing first. So the attenuation of the Enchroma filter includes a notch which coincides with the point where the L and L prime cones are most similar. So in the McLeod-Boynton space, it's worth remembering as we go on that the center is the achromatic point, and towards the outer edges show the more saturated signals, indicating a more saturated hue. So as we go forward, we're looking at the effect of this notch on chromaticities in the McLeod-Boynton space and looking for where the chromaticities are in relation to this achromatic center and more saturated outer edge. So to investigate this, we created a physiologically accurate model of colour vision, which is basically a mathematical representation of each stage of colour vision processing at the retina. So we start with the illuminant with the power at every wavelength. And then we multiply this by the surface reflectance of a surface we hypothesize our observer is looking at. Now, taking the light of the illuminant that is reflected off the surface, we then multiply this by the attenuation of the Enchroma filter to model how the light is affected as it passes through the filter and how this changes the spectral composition of the light. Now, to identify how this is seen by the visual system, we multiply this then by the cone sensitivity of our hypothetical observer, giving us the individual cone responsiveness for this surface viewed under this illuminant with the Enchroma filter. So as we sum these, we can see the overall cone activities and then plot this in our perceptual colour space. So here we see a point in the color space. But what we can do with this model is we can model with and without the enchroma filter. So if this is the chromaticity of a point modeled without the enchroma filter, then we can model the same surface, illuminant observer, with the enchroma filter and represent the shift in chromaticity here. So as we go on in every McLeod-Boynton diagram, the black point is going to represent a surface viewed with our control filter, and the corresponding red point will be the same surface viewed with the enchroma filter. So we went on to model 259 Munsell surfaces to identify how the effect of the enchroma filter changes across all hue directions. And you can see here when we model the surfaces with an LED illuminant, we have gamma expansion across all hue directions. So you can see the red point of the chromaticity when viewed with enchroma is further out towards the more saturated edges of the McLeod-Boynton space. However, we don't see the same trend when we model the appearance, when we model the saturation of these surfaces on a CRT monitor. You can see in almost all cases that the red point indicating the chromaticity with enchroma is closer towards the achromatic center of the space. So we believe this is because the active notch in the enchroma filter coincides with a dip in the gap between the red and green guns of the CRT monitor. So if we take this as evidence that, or a prediction that we should see saturation increase with physical surfaces, we then wanted to test whether this increase in saturation was usable to the visual system. So to do this, we set about a selection of behavioral tasks with 10 deuteranomalous observers that we screened using a anomaliscope. Our first test was a discrimination task to detect any changes in detection threshold. And the second task was the color matching task to identify any changes in hue and saturation superthreshold. So in our discrimination task, we created an array of hand-painted 4AFC stimuli and ran staircase procedures with 7 colors, reducing in saturation monotonically. These were presented manually, going with saturation increasing each time the participant gave an incorrect identification of the target, and decreasing in saturation each time they correctly identified the target. So our model predicts that with the enchroma glasses, the surfaces should appear more saturated. So our prediction was that if they appear more saturated, an observer would need a less saturated chip to identify it. So for example, if a participant was able to reliably identify a chip at saturation level 5 under the control filter, we estimated that the enhancement bestowed by the enchroma filter meant they would be able to identify the surface at saturation level 3. However, we didn't identify this. We identified a small reduction in threshold in the red color, but no evidence of a reliable reduction in threshold in any of the other colors. Our next test was color matching. So this time working super threshold, we wanted to identify any shift in hue and saturation bestowed by the enchroma glasses. So to do this, we took our viewing box and split it in 2 so that participants could simultaneous or within the same setting, view through a control filter and through the enchroma filter. We then presented our target color in one condition and asked them to make a match in the opposing condition. So when we presented our target under the enchroma filter, we predicted this would enhance the saturation of the target and cause them to select a more saturated match from the matching array. So here we have the chips presented to our participants. The red X indicates the target shown under enchroma, with the empty circle indicating the predicted chromaticity this would have because the target is shown under enchroma. So the match our participants actually selected here in the black points shows that in the majority of cases, the participant is selecting a more saturated match and validating the prediction of the model that they are matching to more saturated chips. So we also repeated this in the opposite direction. So this time we presented the target under the control filter and asked them to select a match from the matching array under enchroma. So because the enchroma is supposedly enhancing the saturation of the matching array, we predicted they would select a less saturated chip. So here the X indicates the chromaticity of the target, and the red circle indicates the model's prediction for what they would match it to. And these filled red circles are the matches that they made, showing that they are replicating at least the scale of saturation change that the model predicts. So we're taking this at least super threshold as evidence validating the model's predictions. But what do we expect for the for real world observations? So for this, we used hyperspectral images, which are basically photographs in which we have spectral power distribution for every pixel in the scene, and then ran each pixel through our model. Now here we're describing the scale of the change as a proportion of the overall range of L over L prime plus L. So here you can see we have signal increase generally across the scene, with the biggest increases in the most saturated colors. So for example, in the foliage and particularly in the flowers, but less of an effect in the desaturated concrete. Now we also see saturation increase in artificial scenes with artificially colored objects showing larger boosts than in natural scenes. If we look at the histogram, even though the majority of pixels are showing smaller boosts, some areas of the scene are showing 30 to 40% saturation increase. So in conclusion, we believe this is a strong positive result for the ability of notch filters to enhance anomalous colour vision. Even though we don't find an effect at threshold, we do see a saturation boost super threshold. Although this effect is largely dependent on the surface reflectance, its hue, starting saturation, the illuminance, and also the observer. Thank you very much.